Now let us review some important material from the previous lecture and see how it applies to separable equations. Last week we learned a very important concept of a direction field. And here is an example of a direction field of a separable differential equation. The most important thing about the direction field is that it is tangent at any point to any solution curve of the differential equation. So informally it means that our solution curves, they sort of follow the arrows, right? So if, say, you want to draw a solution that goes here, then it should be something like this. And so on. Recall also that there are sort of two ways to visualize this direction field. One of them is when we draw all the arrows such that the x component is the same, so they kind of all of the same width. And another way to do it is to draw all the arrows so that the length of all the arrows is the same. Sometimes the first one is more convenient, sometimes the second one is more convenient, or sometimes it doesn't matter. But it's good to know that there are different ways to do it. Okay? Well, generally speaking, there is no method to recognize the direction field of a separable differential equation by just staring at it. But there are some ways to do it. Well, some in some partial cases. Like, for example, if the right-hand side does not depend on y. So if the right-hand side is only a function of t, like here. And so you can imagine that this can be thought of as times 1 and y. 1 is a function of y, but whatever. Notice that since the right-hand side does not depend on y, it means that if you change y, then the direction of the arrow is not going to change. And you can see it here. So for example, the arrow at this point is the same as the arrow here, 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 and so on. Well, if you see that these arrows are arranged in rows and columns, then all the arrows in the same column, they are exactly equal. So like here, here, now here, 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 and so on. So the whole vertical sort of row of arrows, all arrows in each row are exactly the same. Or you can imagine that you have two copies of this vector field. One is plotted on a paper and another one is plotted on a transparency. And then if you move the transparency up or down, then the arrows are going to coincide with arrows that are on paper. Alright, so this direction field is invariant under vertical translation. So, and if you see that the direction field is invariant under vertical translation, then you know that it comes from a differential equation where the right-hand side does not depend on y and is only a function of t. But of course, in the same manner, if the right-hand side does not depend on t and only depends on y, then if you think of arrows as being arranged in rows and columns, then all arrows in the same row are going to be the same. So if you look at all these arrows, at all these, say, I don't know, at all these arrows, they are all the same. At all these arrows, they are all the same. So, or you can see it as if there are two copies of it, one on transparency, another on paper, and if you move the one on transparency to the left or to the right, then the direction field is not going to change. So differential equations where the right hand side does not depend on t and is only a function of y are called autonomous. That's a very important term, and in the next lecture we're going to see how autonomous equations can be used to model some population dynamics. And as a matter of fact, usually when differential equations are applied to model some real-life problems, they are usually autonomous equations. Okay? And a little recap quiz for you. So again, pause my lecture, go to this URL, and try to answer a few